Welcome to this explainer. Let's jump right in. Today we're looking at Section A 1.2.5, Constructing Logic Diagrams. We're unpacking the invisible blueprints powering literally every digital decision in your devices. Every single swipe, tap, and automated system uses this fundamental language of logic. So let's break down exactly how we construct the diagrams that form the bedrock of our digital world.
Here is our roadmap for today. We'll be hitting the logic gate alphabet, the rules for processing inputs, drawing real-world solutions, translating math to diagrams, and finally, simplifying those complex blueprints.
Section 1, the logic gate alphabet. Before we can build anything, we need to establish our basic visual building blocks.
So what is a logic diagram exactly? Well, it isn't just some abstract flowchart. It's the literal blueprint used to physically construct digital solutions. When we design a digital system, we use these diagrams to map exactly how logic gates connect, interact, and sequence. And here's the really cool part. These visual representations are meant to be directly transposed into actual electronic circuits. This means the lines you trace out represent literal physical copper wires or microscopic pathways on a silicon wafer. And those distinct shapes, they represent actual physical clusters of transistors designed to process electricity in a highly specific way. It is literally the critical bridge between theoretical computer science and hands-on electrical engineering.
Check out these standard shapes. This is our core visual alphabet, and you absolutely must know these to spell out digital commands. The AND gate is that one shaped like a capital D. The OR gate features that curved, shield-like back. And the NOT gate? That's the triangle terminating in a tiny little circle. Actually, pay close attention to that circle because it's a huge deal. It always implies negation or inversion. So when you run into variations like NAND and NOR gates, you're really just looking at our base AND and OR shapes, but augmented with that inverting circle right at the output. And standardizing these symbols isn't just about aesthetics, it's an absolute engineering necessity. It guarantees that an engineer in Tokyo, a developer in London, and a fabricator in Silicon Valley are all reading the exact same blueprint without a shred of ambiguity.
All right, moving to Section 2, Processing Inputs to Outputs. Having an alphabet is great, but we need strict rules for how these symbols interact.
Logic, much like the physical electrical current it represents, is designed to flow in one specific, non-negotiable direction. You always read from left to right. Your inputs begin on the far left, your processing occurs right in the middle, and your final result emerges on the right. Keeping this strict visual grammar is absolutely paramount. Why? Because it purposefully prevents confusing logical loops, and it allows anyone auditing or debugging the circuit to easily trace the exact manipulation of an electrical signal. You can literally take your finger and follow the path as the signal propagates through each gate, branches off, or merges, right up until it becomes a single decisive output.
Section 3, Drawing Real-World Solutions. Let's take our new vocabulary and use it to physically solve a practical engineering problem. When you sit down to engineer a solution, you typically start from one of two places. You're either translating a word problem into physical gates, or you're translating pure mathematical algebra. With a problem description, you're reading a real-life scenario, like, say, a security alarm, and deducing which gates fit the conditional logic. With a Boolean expression, the logic is already perfectly mathematically defined, and your job is simply to swap the math notation for our visual gate symbols. While the starting points differ, the end goal is exactly the same, a clear, standardized blueprint.
Let's look at a super practical example, an automatic watering system. This system requires specific soil moisture or temperature conditions, but here's the catch: it must only activate during daylight hours. So our problem description dictates the system activates if it is daytime and either the soil moisture is low or the temperature is high. Notice how the soil moisture input S and temperature input T enter from the left and run straight into that curved OR gate. That perfectly handles our either-or environmental condition. Then, the resulting output of that OR gate feeds directly into our D-shaped AND gate, right alongside our daytime input D. If it happens to be daytime and at least one of those other environmental conditions is met, boom, the final output Q fires, triggering the physical water valve. It's just a beautifully clean, highly practical translation of physical environmental states into strict digital logic.
Okay, Section 4, Translating Math to Diagrams. Now we escalate things and construct diagrams directly from the algebraic language of computers, Boolean expressions.
Translating complex math into a physical diagram is really just a matter of layer-by-layer escalation, and it requires a highly methodical approach. Just like regular algebra, we have a strict order of operations. We literally must work from the inside out, paying massive attention to our parentheses, because in hardware design, those parentheses dictate literal execution priority. If a math operation is inside of parentheses, that electrical signal has to be processed first before it interacts with anything else. So the game plan is rigid but straightforward. You plot your main input variables on the far left. Then, you solve your first isolated equation block, that first parentheses, by routing inputs through the required gates. Once that distinct block is built, you move to the next parenthesis, maybe throwing in some inverters. Finally, once all your internal blocks are constructed, you drop in a linking gate. This final gate acts as the grand bridge, pulling the separate outputs from your isolated blocks together into one definitive final output. Stick to this order and you guarantee the hardware mirrors the math flawlessly.
Let's actually build one out step by step to see this in action. Take the equation y equals a and b, or not a and not b. This is a classic construction challenge. Sticking to our rules, we tackle the parentheses first. We lay down our primary input lines, a and b. For our first parenthesis, which is simply a and b, we draw physical lines from a and b directly into a single D-shaped AND gate. Awesome, that isolated block is complete. Now for the second parenthesis, not a and not b. We tap back into our original a and b lines, but this time we route them through our triangle-shaped NOT gates to completely flip their signals. Those newly inverted signals are then fed into a second, separate AND gate. So at this stage, we have two distinct logical blocks operating totally independently. But the full equation demands an OR relationship between them. So for our final step, we have to link them. We take the outputs from our two separate AND gates and route them together into a final linking OR gate to get our definitive output, Y. By methodically isolating parentheses like this, we take abstract algebraic logic and forge it into a literal, physical pathway for electricity.
Section 5. Simplifying complex blueprints. Finally, what happens when these logic diagrams start layering not just into the dozens, but into the millions?
Okay, don't panic, you won't have to decode this massive fast adder circuit today, but the sheer density of it proves how combinations of our simple visual alphabet scale up to build modern computing architectures. Every single microscopic component in a complex adder is really just an AND, an OR, or an XOR gate. Engineers just compound them in incredibly clever cascading structures to execute massive mathematical operations at literal lightning speed. But, as you can imagine, scaling up creates entirely new physical engineering problems. As you add more gates, the architecture gets inherently messy, it becomes highly expensive to manufacture, and it absolutely guzzles power.
Because these computational systems get so massive, engineers rely heavily on Boolean algebra rules to systematically simplify these diagrams way before a single physical chip is ever fabricated. We use techniques like Carnot maps to visually group logic states and quickly hunt down redundant gates. Or we apply mathematical theorems like the commutative law, which proves that rearranging the order of certain inputs won't change the final outcome, which can seriously clean up a wiring layout. The ultimate goal here is extreme efficiency. If you can mathematically prove that a complex 20-gate circuit does the exact same thing as a streamlined 5-gate circuit, you're obviously going to build the 5-gate version, right? Systematically reducing the physical gates shrinks the footprint on the silicon wafer, minimizes signal latency, and drastically lowers the required power draw. It's a total win-win.
To wrap this up, think about this. The laptop or smartphone you are looking at right now contains literally billions of these microscopic logic gates. Billions! And yet, every single one of them was mapped out using the exact same visual alphabet, flowing from left to right, processing inputs to outputs that we just covered today. I really hope this explainer has given you a fresh appreciation for the intricate, beautifully structured logic hiding just beneath your screen. What kind of logic flow is firing off the second you tap the glass? Thanks for joining me.